Okay students, welcome to this particular session. This is the last topic of dimensional analysis. We have discussed about the dimensions of a physical quantity, the principle of homogeneity of dimensions. Then we have discussed the uses of dimensional analysis. We have discussed some numericals as well. Lastly, we will discuss the drawbacks of dimensional analysis. Right? Let's start with the drawbacks. Okay. So the first drawback is dimensional analysis cannot be used to determine the value of k, small k. It cannot be used to determine the value of k, which I have told you numerous times. It is a dimensionless constant, isn't it? The value of k is to be determined either experimentally or through some other method. But dimensional analysis cannot be used to determine the value of k, which is constant of proportionality, and it is a dimensionless constant. So this is the first drawback of dimensional analysis. Second, it cannot be used to derive the composite relations. It cannot be used to derive composite relations. Composite relations, like this. Composite relations means containing more than one terms. The terms are connected either by subtraction or addition between them, like v is equal to u plus at. Look, right hand side it contains two terms connected by this addition sign. Then s is equal to ut plus half at square. Then 2as is equal to v square minus u square. In all these cases, the formula contains more than one term on one side of the equation, right? And they are connected by either addition or subtraction. So these are known as composite relations. These are known as composite relations. So such relations can't be derived using dimensional analysis. It can be derived in parts. In parts you can do it. In parts you can derive the expressions. But again, then the question will arise, what will be the sign between them? Positive or negative? So, the dimensional analysis cannot be used to derive composite relations. These are the examples of some composite relations. Right? This is the second drawback. Third drawback. There are certain mathematical expressions or formulas which involves trigonometric functions, which involves exponential or logarithmic functions. Now, exponential, logarithmic functions, trigonometric functions, they all are dimensionless, isn't it? So all those relations involving logarithmic functions, trigonometric functions or exponential functions can't be derived using dimensional analysis, right? Like ascent formula, it's given by 2t cos theta divided by r rho g. It is the ascent formula. This is one of the formula which we'll study later on. So this formula involves this trigonometric function. So dimensional analysis cannot be used to derive this particular formula. Or there are some other relation as well, like y is equal to r sine omega t. This equation, it involves trigonometric function. It can be used to verify whether it is dimensionally correct or not. But that is not the sufficient condition to prove that this formula is valid or not. Because in place of sine omega t, if I substitute sine by cosine function or tangent function or cotangent function, then also the formula will remain dimensionally correct. Isn't it? So basically, dimensional analysis cannot be used to derive those formulas involving trigonometric functions, logarithmic functions or exponential functions. Fourth, This is a very, very important point. We'll discuss it with the help of a numerical. Fourth is basically, in a physical phenomenon, if a physical quantity is dependent on more than 3 other physical quantities, then in such a case, dimensional analysis cannot be used to derive such formulas or such relationships. Right? I repeat, for dimensional analysis to derive a relationship between various physical quantities, a physical quantity can be dependent on at most 3 other physical quantities, not more than 3. In case a physical quantity depends on more than 3 other physical quantities, then such relationship between physical quantities can't be determined using dimensional analysis. Right? I will illustrate this point with the help of a numerical. We'll simply do it. First, let's discuss the drawbacks first. Right? So that's the fourth drawback. Fifth one, just now I've told you, even if you replace cos theta by sin theta, tan theta, cotangent theta, then also this will be dimensionally correct. But the formula will be invalid, isn't it? So what I mean to say is that the equality of dimensions on the two sides of an equation is indeed a necessary condition, but not the sufficient condition for the physical relationship to be valid. It is because you are aware there are various physical quantities which, although they are different, but might possess the same dimensions. I'll give you some examples. Like momentum, impulse, they are both different physical quantities, but both have the same dimensions. Similarly, modulus of elasticity, stress, pressure, these all are different physical quantities, but all these quantities have the same dimensions. So basically, equality of dimensions on both sides of a given equation is a necessary condition, but not sufficient condition to validate the relationship between these physical quantities. So students, these were the 5 drawbacks of dimensional analysis. Let us recapitulate it, right? We have discussed 3 uses, now we are discussing 5 drawbacks of dimensional analysis. The first drawback was, or rather the first drawback is, dimensional analysis cannot be used to determine the value of k, which is dimensionless constant. The value of k is to be determined either experimentally or by some other method. Second, these are composite relations involving addition or subtraction between 2 or more terms. So such relations cannot be derived using dimensional analysis. Third, those relations involving trigonometric functions, logarithmic functions or exponential functions can't be derived using dimensional analysis. Fourth one, if a physical quantity is dependent on more than 3, I repeat, more than 3 other physical quantities, then such formulas or relations can't be derived using dimensional analysis. And the fifth one, based on the above facts, there are various physical quantities which, although are different, but have the same dimensions. So what I mean to say is that the equality of dimensions on the two sides of the equation is a necessary condition, but not sufficient condition to validate the correctness of the relationship. So students, these are the 5 drawbacks of dimensional analysis. Now let me illustrate this fourth point, right? So in order to illustrate the fourth point, I'll consider an example. Let us consider a physical phenomenon where a physical quantity is dependent on more than 3 physical quantities. More than 3 physical quantities, right? So what to do is, let us consider the force acting on a body. Let us consider a force acting on a body be dependent on its mass. How it depends, I don't know. We can write it as A. Let us consider it depend upon its speed with which it is moving. Let us consider it depends upon its radius of the circular path which it follows. Let's also consider it depends upon, say, universal gravitational constant, right? So in this case, this physical quantity force is dependent on more than 3 other physical quantities, right? Such relations can't be derived using dimensional analysis. That is what I am going to prove, right? So what will do? What's the first step? We can write it like this, right? Next step is to substitute the dimensions of these physical quantities. Force, it is mLT minus 2. Mass, it is m. Velocity, it is lt minus 1. Radius, it's L. Gravitational constant, it is m minus 1, L3 t to the power minus 2. Clear? Let's rearrange the terms m to the power a minus d, right? L to the power b plus c plus 3d. T to the power minus d minus 2d. Now we need to equate. As per the principle of homogeneity of dimensions, isn't it? The dimension on both the sides must be same. So what do we get? First equation is a minus d is equal to 1. This is the first equation. L to the power. In the right hand side it is b plus c plus 3d. Left hand side it's 1. This is the second equation. What's the third equation? T to the power, it's minus b minus 2d. And over here it's minus 2. So these are the 3 equations we obtained, right? Now observe these equations. Can we solve them? Mathematically, it is impossible to solve for the values of a, b, c and d. Why? Because it involves 4 variables a, b, c and d. 4 variables. And we are having only 3 equations. So it is impossible to solve it and get the value of a, b, c and d. You can try it, you will never be able to get the value of a, b, c and d. In case there are 2 variables, 2 equations are required. In case there are 3 variables, 3 equations are required. And in order to solve 4 variables, 4 equations must be required. But here we are having only 3 equations. So this is the drawback which I am talking about. So remember students, dimensional analysis cannot be used to derive relation when a physical quantity is dependent on more than 3 other physical quantities. Clear? Okay. Let's discuss a numerical based on conversion of one system into another. Right? Let's consider an example. Let us consider the density of a body. The density of a body is given to be 8 gram per centimeter cube. Obviously it is in CGS. What will be the density? This is the density in a new system. Where the fundamental units of mass and length are 20 gram and 5 centimeter respectively. Right? So I am repeating the question, it's a very interesting question. The density of a substance or a body is given to be 8 gram per centimeter cube. It's a CGS system. Density is mass over volume, right? What will be the density of the same body in a new system where the fundamental units of mass and length are 20 gram and 5 centimeter respectively, right? How to go about it? Let's see. So, this is system 1, which in this case is CGS. This is the new system, system 2, which we are not aware of. In the CGS system, the numerical value of the physical quantity is 8. In the new system, the numerical value is to be found, right? Here, in the CGS system, the basic units are gram, centimeter, second. So M1 is 1 gram, L1 is 1 centimeter, T1 is 1 second. Time we don't require because density is independent of time. So the dimensional time is 0, right? So we don't require. While in this new system, as per the quotient, the basic unit of mass is 20 gram. The basic unit of length is 5 centimeter. Time is not given and it's not required even, right? It is independent of time. Now density, students, it's given by mass over volume. So that is, what will be its unit? Gram. In CGS it is gram per centimeter cube. So dimensional formula for density is m1 L to the power minus 3 t to the power 0. This is the dimensional formula. So what about the value of ABC? A is 1. A is the dimension of mass. B is the dimension of length. And C is the dimension of time. Right? These are the values we require. Clear, students? Now, in order to obtain the value of N2, what's the formula? N2 is N1. M1 by M2 to the power A. L1 by L2 to the power B. And T1 by T2 to the power C. Let's substitute the values. N1 is 8. M1 is 1 gram. M2 is 20 gram to the power 1. L1 is 1 centimeter, L2 is 5 centimeter to the power minus 3 to the power 0. Now look, it is independent of time. So anything to the power 0 is 1, right? You need not to write this even. So 8 into 1 by 20 to the power 1 would give you the same value. 1 by 5 to the power minus 3. So you can write it like this: 8 into 1 by 20 into 5 to the power 3, right? Or in other words, 8 into 125 divided by 20. So it will give us 2, 4, 5, 25. So it will give us 50 units. So students, the value of the density of the substance in this new system, where 20 gram and 5 centimeter are the fundamental units of mass and length, is 50 units. I sincerely hope you have understood the concept involved. So students, again I repeat, do practice more and more numericals. It is only then the confidence can be achieved, right? So all the best. We'll continue with the next chapter in the next session, right? So till then, goodbye and do take very good care of yourself.